Welcome to this unit all about mild hybrid. Now, mild hybrid might be a term that's new to you, or actually you may have heard it before. So in this unit, we're going to go through mild hybrid, what is it? We're going to look at some different electrical configurations on how mild hybrid vehicles are assembled. But before we start with mild hybrid, I want to just revert back a little bit to a standard internal combustion engine, or ICE for short. Now, on that ICE vehicle, we have our three major key components. We have the 12-volt battery, we have the starter motor, and we have the alternator. Battery electricity from the battery is provided to the starter motor, starts the combustion engine, and then from there onwards the alternator takes over and replenishes the power back into the battery. So we end up with this really sort of nice cycle. So how does this differ than mild hybrid? Well, so with mild hybrid, we're going to combine the starter motor and the alternator into a single unit. Now they've got different names, but common names are the belt starter generator, the BSG, or the integrated starter generator, the ISG. They do exactly the same job, just different names for different manufacturers. So we're going to start off first with our integrated starter generator, our belt starter generator. It's usually positioned on the front of the engine, kind of in the same place that you'd expect your alternator to go. It is belt driven around the crankshaft, and that's how it's able to supply energy from the motor into the engine, all driven around the belt driven crankshaft. Now these motors tend to be around about 7 to 10 kilowatts in power, so much more powerful than a traditional 12-volt starter motor. So we start off with our belt starter generator, and if we follow the wire back, you'll see that we come to a 48-volt battery. Now, traditionally with the mild hybrid systems, we run in one of three voltages. We will start with either 12 volts, 24 volts, or 48 volts. Now, you might be asking yourself, why the three different voltages and why stop at 48? Well, if we take one vehicle to begin with, something like an Audi, that actually runs a 12-volt mild hybrid. So we have two 12-volt systems, we have different controllers in there, similar to a traditional combustion engine, but with almost two separate systems. Mazda, for example, use a 24-volt mild hybrid system, but the majority of manufacturers going with mild hybrid are going with 48 volts. Now there's a reason that they do 48, and that is because under 60 volts, there is a different set of regulations about the kind of cables you need, the kind of levels of protection, the levels of safety. And if we remember back from our electrics training, as the voltage increases, the current decreases. And if I can decrease the current, I can decrease the size of all the cabling that I need. Let's go back to our mild hybrid system. Now we're going to assume for this example that we're at a 48 volt system, although as you've seen other voltages are available. So we've got our belt starter generator, and then as we come down, we're going to hit the 48 volt battery. That's where the belt starter generator charges. Moving on from the 48 volt battery, we then have a DC to DC converter, and this steps the voltage from 48 DC down to 12 volts DC. So you'll see here that the belt starter generator doesn't charge the 12 volt battery directly, it charges the 48 volt, and then the voltage is stepped down to keep the 12 volt battery topped up. Now, as you can see from the diagram on screen, the 48 volt battery is there to simply supply the engine with additional power. It's there to perform the role of starting the engine and also supplying the power to the rest of the vehicle. The 12 volt battery still does every job it does today. It powers the lights, the wipers, the heated windows, everything your normal system does. But it's backed up by that 48 volt system carrying out some of the heavier duty tasks. Now it's possible, of course, as you can see here, that we don't have a second 12 volt battery. We still have this 12 volt circuit, but a physical battery isn't required. We simply take the 48 volt, we use a DC to DC to step down, just like the previous system, but we just don't require the 12 volt battery. We power the systems directly from the DC to DC converter. Now we can do this because all of the big items, such as the starter motor and alternator, those items now are instead used on the 48 volt system with the starter generator. So the only thing on the 12 volt system is the ancillaries inside the car, which are on the whole generally a lower current items. So the diagrams have been front wheel drive, but what about if you have a rear wheel drive car? Well, in essence, nothing really changes. You can see here that if we turn the engine round and we have rear wheel drive system, the belt starter generator or the integrated starter generator still remains on the same place within the engine, belt driven around the crankshaft, just the engine direction has changed. So in terms of system operation, it's exactly the same. The lithium ion batteries that are commonly fitted to these 48 volt systems, their places can move. You're seeing from the example here it's at the rear of the car, but actually it can quite happily be at the front of the car within the engine bay, providing there's enough space. So you've seen the basic operation now of the 48 volt system, but what about if we want to take things a little bit further? We've now got this newfound power, this 4 times amount of power in the 48 volt than we did in the 12 volt. So we can now start to run other heavy power systems directly from the 48 volt battery. Let's add an electric supercharger to the mix. So here you can see that the 48 volt system runs the starter generator and it runs an electric supercharger. Now, what you may, contrary to belief, we sometimes have an electric supercharger and a turbocharger run off the exhaust system as normal. At the moment, we're not looking at replacing them completely, but we are looking at supplementing it. Now, of course, so with a turbo engine, they're always subject to turbo lag, and this is something that the 48 volt system with electric supercharger can address. During low engine speed, the electric supercharger can begin to build up the boost within the system, and then when the exhaust gases are exiting the engine quick enough, the mechanical turbo spins round and generates the boost required for the engine. Having a system like this almost completely eliminates turbo lag and really gives it a much better driving experience. Coupled with the fact that the belt starter generator is giving up to an additional 10 kilowatt of power to the crank, that means we can get things moving much quicker. So we're using the 48 volt system for the starter generator and potentially an electric supercharger. But what about other systems which are high current draw systems? As we're adding complexity to the vehicles, more wiring, more computers, and especially around hybrid and electric batteries, we're starting to increase the vehicle's weight. Now, of course, any addition to the vehicle's weight is going to have a negative impact on the way it handles. So because of this, manufacturers are looking for the ways of improving their suspension systems to almost hide the weight and still give that really good driver feeling. Now, one way of doing this is adding in active anti-roll bars. Now, rather than having a solid roll bar from side to side and the characteristic of the vehicle roll all depends on the twist of the bar, instead that we can have a 48 volt motor on each side, and that motor is giving the resistance to the roll bar to simulate a traditional roll bar. But if we're traveling on a motorway or a very smooth road, the active anti-roll bar system will back off. It will allow the vehicle to bounce a little bit because it wants that smooth running. Then, when the driver pitches into a corner hard, the active anti-roll bar firms up and gives that driver that sporty feeling. So having this system almost gives the best of both worlds. It allows you to take a slightly heavier vehicle and still give it that nice smooth ride, but still give it the great cornering handling characteristics. Now, the 48 volt system in this can be used in 2 ways. You can either have an active anti-roll bar system, as you can see here, but you could also have an active spring and damper system using 48 volt motors and pumps. Now, those systems, as the spring compresses, will give force back into the suspension coil and can change the firmness using a 48 volt motor and pump to try and suit the driver's needs. Perhaps the driver has selected a more sporty dynamic drive, or they've selected comfort mode because they're carrying passengers. Having these systems on the 48 volt architecture means that we can really lower the current and we can put these higher power items on thinner cables, and ultimately they can be more efficient. So hopefully you found this section on mild hybrids interesting. Remembering that we've got 12 volt mild hybrid, 24 volt mild hybrid, and finally 48 volt mild hybrid. And they can power everything from the belt starter generator to an electric supercharger, all the way through to an active anti-roll bar or suspension system. Welcome to this section all about full hybrids. Now, by now, hopefully you've completed the mild hybrid unit. And remembering that mild hybrid runs from around 24 to 48 volt, with the ceiling being at 60 volt DC. Remember that below the 60 volt DC limit, there are different regulations based on safety and cabling and insulation. So generally that's why manufacturers stick to 48. But in this module, we're going to look at full hybrid, traditionally hybrid vehicles above 60 volts. Now, on average, the entry-level hybrid vehicle starts around the 200 volt mark. So in this first example, we're going to look here at a hybrid architecture, almost like the basic layout of a hybrid system. The first example we're going to use is the hybrid that's probably been on the road for the longest. That is the Toyota Prius system. So Toyota's hybrid synergy drive. This system has two electric motors in the front axle, MG1 and MG2. MG1 being the smaller motor, which starts the engine and charges the vehicle's batteries, and MG2 is the one that drives the road wheels. From the motors, we have two sets of three-phase AC wires. And you'll notice from the diagram that they leave and they all merge at the converter. Now this unit is actually an inverter-converter unit combined. And what its main job is to do is to take the AC three-phase from both motors, MG1 and MG2, and combine them and convert them into DC single-phase. Because any battery cannot be charged using AC. It must be charged using DC. Now that power from the 200 volt battery in this example then goes to a DC to DC converter through to the 12 volt battery. So you'll notice that whenever we're starting the engine or using the electric motors to drive the wheels, that none of the power comes directly from the 12 volt. We take it from the 12 volt, we have a DC to DC converter, and then we've got the main 200 volt battery. So at all times, the DC to DC converter is charging the 12 volt battery, which is then powering the ancillaries of the vehicle, such as the dashboard, the headlights, the wipers, and all of the other 12 volt components on that 12 volt architecture. So let's change the example. What about if we weren't looking at a Toyota Prius? Let's look here at a Hyundai Kona hybrid, which of course is a very similar system to the Kia Niro hybrid. And this system, instead of having the two electric motors inside the gearbox working together, this actually has the one electric motor, the larger electric motor in the gearbox, and the other electric motor is external, similar to the mild hybrid systems. It's an external AC three-phase belt starter generator. Now you've seen a few different layouts. We've looked at the Toyota Prius system as a basic overview. We've looked at the Hyundai Kona hybrid as a basic layout. The last one, of course, is the rear-wheel drive. So this example here is something like a Mercedes C-Class. So being a rear-wheel drive, we have an electric motor in the transaxle, in the gearbox. The rest of the system remains the same. We still have the inverter converter. We still have the DC to DC step down, just in a slightly different configuration, just because it's rear-wheel drive. The main components and the main system design and the system operation, they kind of remain the same. So now you've completed this section on hybrid vehicle layouts, let's move on to the next section and we're going to look at plug-in hybrid vehicles. Now the biggest difference with plug-in hybrid electric vehicles is two things. The first is, traditionally the electric motors are larger, and that's because a plug-in hybrid vehicle is like a hybrid but designed to run in electric-only mode for extended periods of time. This can be anything between 15 to 30 and beyond miles. Now because these systems are designed to travel in electric-only mode, they will normally have two key items which are larger. That is A larger electric motor, and B, a larger battery. So other than having a larger battery and a larger electric motor, what's different? Well, of course, plug-in hybrid, everything's in the name. I need to be able to recharge it externally. And because of that, I will have a plug on the outside with either a Type 1 or Type 2 connector, and we'll also have what we call an onboard charger. Now remembering that the same power that's in our house is the same power that comes from the electric motors. It's an AC power source. So what our onboard charger has to do is it has to take the voltage from the house and it has to convert it from AC to DC ready for our batteries. It also might be that the voltage from our house isn't the same voltage that's in the batteries. So quite common to have 240 volt AC in the electrical sockets, but a 400 volt DC battery. So in that case, the charger has two jobs: to step up or down the voltage and also convert from AC to DC. And that is the role of the onboard charger, as you can see here. Now, this particular one here has an AC single phase input. That means that, like most houses are AC single phase, that it can take that power, do the conversion and begin charging the batteries. But if we change it over, the next one has an AC three-phase input. So whilst a little bit more common on electric vehicles, plug-in hybrids could still have this technology. And the only big advantage, of course, is that it means that we can charge the batteries even quicker. The only difference from going from single phase to three phase is higher current, and we can charge the battery even quicker. In the hybrid and plug-in hybrid technology diagrams you've seen here, then there is a couple of differences, and I want to introduce you now to the system used on the BMW 225xe. Now, this is a traditional combustion engine driving the front wheels. If you look, we've got a belt starter generator, AC three-phase, attached to the engine. And on this example, we've actually got an e-axle on the rear. So with the combustion engine driving the front wheels and the e-axle driving the rear wheels, this turns into a all-wheel drive vehicle. So the belt starter generator, through the integrated starter generator and the inverter converter, charges up the high voltage battery. That power can then be used and sent to the e-axle to begin charging and using that power. Now, because it's a plug-in hybrid, we have an external plug. This example here is a single phase charger unit, and that encompasses the topology there of the 225xe, the slightly unusual plug-in hybrid system, but still very effective. As you've seen, we've covered mild hybrid, standard full hybrid, plug-in hybrid. It's time to now look at electric vehicle. The good thing is electric vehicle can often be far simpler. We have a much larger battery because, of course, we have no combustion engine to take over at a later date. As you can see, the same components exist. We have the inverter converter unit that does the AC to DC conversion from motor to batteries. We have the DC to DC, which drop it from the 350 or 400 volt higher voltage battery down to the 12 volt battery. So all in all, electric vehicles tend to be a much simpler system. Now, just as the plug-in hybrids had either a single or three-phase input going into the onboard charger, the same is true for electric vehicles. Vehicles such as the Renault Zoe, the Tesla Model S or X, these vehicles can use three-phase input, meaning that their charge rate can be anywhere between 2.2 kilowatts all the way through to 22 kilowatts. We're going to cover that a little bit more in the next unit. But what about if you put one of these vehicles on a ramp and you lift it up in the air, take all the coverings off, and you don't see the three-phase cabling? Well, in this example here, we're looking at a Tesla Model 3 dual motor all-wheel drive. Now, this has two sets of DC cables coming from the battery. The battery, of course, is 350 or 400 volt DC. And the DC cables go to the motors, and the motors have inside them the inverter converter units. So you only see the DC cabling going to the motor, the inverter converter is bolted onto the side, and that conversion from DC to three-phase AC is done internally within the motor housing. This one here has, of course, a motor at the front and a motor at the rear to give it more power, more stability, and ultimately a much better drive. Lastly, we're going to look at a different vehicle. We're going to look at a vehicle that utilises the 12 volt system, just like every electric vehicle, hybrid and plug-in hybrid. We're going to look at the vehicle that utilises a high voltage system, the same as every hybrid and plug-in hybrid. But it is possible to have three voltages on one vehicle. We have the 12 volt system for running all the ancillaries. We have the high voltage system for running the electric motor, the air conditioning system. And we also have a 48 volt system for running the active anti-roll bars, as you saw in the mild hybrid unit. So here you can see it is possible to have the three voltages, the high voltage, the mild hybrid voltage, and the low voltage all on a single unit, on a single vehicle. Now for this we'll have different colours. We'll have the orange, the brightly coloured wires for the high voltage system. You will have blue, purple or grey for the mild hybrid system, and then all of the rest of the colours that are used, red, black, generally for the battery, and all the other systems they can use different colour wires on the 12 volt system. So thanks for watching this unit. Hopefully at this point now you're up to speed on everything hybrid, plug-in hybrid and electric.